Okay, so we are going to cover neutron radiography, one of the NDT method as part of basic examination syllabus. So coming to the introduction, so you can see the title Neutron Radiography. So earlier we are familiar with X-ray radiography, gamma radiography. So you already did maybe some jobs with X-ray machines or the gamma ray equipment. So we call it as a gamma ray radiography, meaning we are utilizing the gamma rays, or we are artificially producing X-rays and we are taking the radiograph. That technique we call as X-ray radiography or gamma radiography. But here the title itself saying neutron radiography. So what is a neutron? It is nothing but a nuclear particle. If you see atom, so inside you have a nucleus. So inside this nucleus you have both proton and neutron. So proton is having a positive charge, P for positive charge, and neutron is a neutral. There is no charge. So this neutron we are using to take a radiograph, meaning with the help of neutrons we are capturing the film, meaning we are recording on the film. So that technique we call as a neutron radiography. So what is the main difference between gamma and X-ray? This X-ray and gamma ray is a wave, electromagnetic radiation. It is a form of wave. But when you see the neutron, it is nothing but a particle. Same like a proton, this is also a particle, but there is no charge. So X-ray gamma ray is nothing but a wave, but a neutron is a particle. So here totally the mechanism is a slightly different. If you use a film, radiographic film, industrial film, so if it is exposed with a light or radiation, so you will get a darkening like the film density. Based on that you can interpret. But here how we can use the particles. So here we cannot directly use the regular films. We need to use some screens. We call as a metal screens. So you can use some metal screens and the metal screen will interact with the neutrons and they release some energy. That energy will expose the film. Okay. So neutron radiography is one of a non-destructive imaging technique that uses thermal neutrons. Why they mentioned thermal neutrons? Because when you try to produce the neutrons, you will get a variety of neutrons. We call as a fast neutrons, cold neutrons, epithermal neutrons. Based on their energy range, we call with the different names. But why we mention about thermal neutrons? Thermal neutrons is having certain energy range and they are very useful for NDT purposes. You have fast neutrons but no use. So when you produce a neutrons in a nuclear reactor, they are all having a very high energy, but NDT point of view they are useless. So we need to slow down their speed, then we can make useful for our applications. So that's why they call with a name called as a thermal neutrons, meaning when they reduce their energy to certain level, we can call them as a thermal neutrons. Okay. So unlike X-ray, neutrons only interact with atomic nuclei because these particles belongs to the nucleus. So they will interact with the atomic nuclei. But if you see X-ray, so they will interact with the outer shell electrons. If you see PMI, positive material identification, so they will hit the outer orbiting electrons and then you will get a spectral lights. Okay. So if you see this, if you take a normal X-ray, what happens? Like you cannot see the entire things clearly. For example, this is a bullet. If you have something inside, if you take X-ray, sometimes you cannot see the details very clearly. For example, if I fill with some liquid, right? So if you take X-ray, you cannot see because it is a metallic portion, and you can just see only metallic shell outside. But if you take neutron radiography, you can see everything very clearly, especially the low dense material you can able to see very clearly. So it's a quite opposite to X-ray. I will show you later the pictures, then you can realize. So neutrons will be strongly influenced by hydrogenous materials, plastics, explosives, oil, water. So for example, if you are doing X-ray gamma ray, so if you want to see the information very clearly, so what we are doing, like we will place a lead numbers. Why we are keeping lead numbers? Because are highly attenuating materials. So when you put a lead numbers on the film, so the X-rays cannot penetrate and you can see them like a white color density. But here the same way, in place of neutrons, if you put water or any hydrogenous materials like low dense materials like plastic, graphite, paraffin, or any explosive materials, all these are all low dense materials. If you keep, so the neutrons cannot penetrate through them and you can see the density variations very clearly. So like for example, if you want to stop X-rays, you can put a lead sheet, but here you put a water, so they will be stopped, or you put any plastic layer, or you put wax, so they will be stopped. But if you put a very thick lead brick, so what happens? The neutrons can easily pass through it. So it's a quite reverse to X-ray. So in X-ray, the lead sheet will stop X-ray. But here the neutrons can easily penetrate through the lead sheet. But if you put a small paper, so the neutrons will be stopped. But X-ray can easily pass through the paper. If you put your hand, so the X-rays can easily pass, but neutrons will be stopped because of water, hydrogenous materials. So NR is a valuable non-destructive testing, which is ideally complements conventional radiograph. Complements. Initially, they thought like NR is a competitor to radiography, but later they realized that NR is a complementary, meaning wherever X-ray fails, so there we can use NR. So it's a quite opposite. So X-ray cannot, so then NR will do. But NR will cannot, then X-ray will do. So like you can both complement to each other. Okay, both helping to each other. One is X-ray and another one is NR, because it's a quite oppositely working with the X-ray. So there are various kinds of neutron energies, but only thermal and cold neutrons are very useful for NDT applications. So you can produce fast neutrons, epithermal neutrons, variety of neutrons you can produce, but for our NDT purpose we just need to use only thermal and cold neutrons. Okay, so here neutron absorption is higher in light density materials than in heavy materials. For example, if you are dealing with X-ray, so if I put a titanium or if I put a lead sheet, what happens? X-ray will be stopped. If too many X-rays coming here, so only small portion will come out because of attenuation. But here, if you put a low dense material, so this one is a high density, lead sheet is a high density material. But if I put a low dense material like water, graphite, so what happens? The neutrons cannot penetrate through this. Okay, so neutrons will be stopped. But if I put a lead sheet, very big lead sheet, so the neutrons can easily pass. Okay, you see here lead sheet of very heavy thickness, but lead neutrons can easily pass because it's a nuclear particle and it can easily interact with high atomic elements. So for example, finding a lead in a paraffin block or a needle in a haystack would work for X-ray. For example, you take a haystack that is nothing but a grass. Inside it there is a needle. So if you take X-ray, you can see the needle easily because grass is a low dense material and needle is a high dense material. But if you go with the reverse way with a neutron radiography, so the grass you can see very clearly, but needle is missing. So something like quite opposite you can see here. If I take X-ray, I can see the needle, but if I take neutron radiography, I can see this, but I may miss this needle because needle is a high dense material compared with this low dense material we can able to see very clearly. So you can see here. So the best one, if you take NR, so you can see this one very clearly, the stick you can see very clearly. But if you take X-ray, the metallic pins you can see very clearly, or this needle you can see very clearly with X-ray. But in NR it is a quite opposite. If you see this camera old type model, you can see this plastic one. If you take X-ray, you cannot see these plastic portions, but with NR you can see all the plastic things very clearly because plastic is a low dense material, so you can easily stop this neutrons. It can easily stop the NR neutrons, and you can able to see the density very clearly. That's why neutron radiography is a bit famous. And if you see this one metallic idol, and if you take X-ray, you can see only metallic portion. But if you take NR, inside the coconut coir, all the dust particles, everything you can able to see very clearly because these are all low dense materials. Okay, so low dense materials you can able to see very clearly. And if you see this one and NR, so this one is a weed and this one is a cello tape. You can see the masking tape kind of thing, tape. This is a loudspeaker actually, so you have a small wire inside, and this is a cello tape. Everything you can see very clearly. But if you take X-ray, this plastic one we cannot see very clearly, right? But here we can able to see very clearly with neutron radiography. Okay, you can see all the dust coir, coconut coir, or dust particles, everything, any low dense materials. If you put water inside, you can able to see very clearly. But here you may miss it. So coming to the setup, so if you want to take a neutron, so neutrons actually particles, so they will go in different direction because of the scattering. So we need to collimate them, we need to allow them in a certain direction. That's why we use a collimator. And in the exam there will be one question on this collimator. What type of collimator we are using? We are using a divergent collimator. So what is the meaning of divergent? So like you see here, so here you are spreading the beam like this. So this one we call as a divergent beam, meaning small beam you are making a bigger size, you are covering a larger area. So this one we call as a divergent. What about convergent? Convergent is a reverse. So if you have a bigger one, so it will go to this. Convergent is a reverse one, but most of the time we are using a divergent one. Why we need this kind of divergent collimator? Because you want to cover the larger areas, especially if you take RT, if you want to take a radiograph with the panoramic techniques, like if you want to cover three portions at the same time, suppose 1 2 3, you want to take three shots. So what you can do, you can use a divergent collimator so that you can cover the three areas in a single shot. You can cover three exposures. So if you want to cover the larger areas, you need to use this divergent collimators. So in the exam they used to ask one question on this. So you can see this one is a sample flower. So here neutron radiograph of a flower shows the method's ability to imagine thin biological samples. You can see everything very clearly. Small details also we can able to see on the screen. But if you take RT with X-ray, gamma ray, you cannot see this one very clearly. Okay, so the detector behind the same. So detector, because these are all particles, so you have a metal screen, and then inside you can see keep the film. The metal screen will interact with the neutrons and they'll produce some energy, and then the film will get exposed. So if you've seen the typical setup, so you have this divergent collimator, and there is one thing called as a moderator. Why we need to use a moderator? If you produce a neutrons, they are all having a very high energy, we call it a fast neutrons, but fast neutrons are not useful for NDT. So we need to reduce their speed, we need to slow down. So that slow down material is nothing but moderator. Moderator is nothing but like a speed breaker. So if you want to control their speed, you need to pass them through the moderator. So what type of moderator we use? Like water, graphite, carbon, paraffin, like these low dense materials will act like a moderators. So when you pass these high fast neutrons through this moderator, they will be slowed down. Then you need to collimate, because these particles will scatter in different directions. So you need to collimate them, and then they will be exposed to this object and then recorded on the screens. Okay, but as these are all particles, you need to have a very good adequate biological shielding, meaning the particles should not come outside, because dangerous, very high speed, and dangerous if they exposed to the human body. Okay. Then coming to the working principle, so as I mentioned, right, so the mass attenuation coefficient is a slightly different. For example, lead, you have a different value. So water, you have a different value. Hydrogen is a different value. In X-ray, so when you keep uranium or any high dense materials like lead, titanium, then X-rays will be stopped. But here, low dense material like hydrogen, lithium, beryllium, like low dense materials, they will stop the neutrons. So that is what we call as attenuation coefficient, is a slightly different. And here we are dealing with the nuclear related things, because it is a neutron, which is a nucleus particle, and hydrogen bearing compounds are clearly imaged. If you want to take a radiograph for any hydrogenous materials or any radioactive samples like uranium or any radioactive isotopes, if you want to take radiograph for those materials, we can use this technique. Later with the techniques I will explain clearly. Then neutron radiography is the only one radiographic inspection method for radioactive objects. For example, if I bought a capsule, this one is like a cobalt 60 capsule. So there is a small capsule inside. I bought this source. I want to take a radiograph of this. So if you keep a normal film, what happens? So this one is already emitting radiation. The film immediately will get exposed, because the radiation capsule is already having a very high energy. So in that case, what we need to do? So we need to use a screen, metallic screen, and instead of sending the X-ray gamma ray, we can send the neutron particles through it. Then what happens? The neutrons will pass through the radioactive material and then impinging on the screen, and the screen in turn converts as a radioactive material and produces the image. I'll explain with the techniques. There are two techniques. One is a direct technique, other one is indirect technique. Okay, so you can see here. So if you see in this X-ray gamma ray, so some of the high dense materials they will stop X-ray gamma ray. But when it comes to neutron radiography, these low dense materials like hydrogen, boron, water, beryllium, these materials will stop the neutrons. So quite opposite. In X-ray gamma ray, we put lead sheet and they will be stopped. But here you put boron, or you put water, or you put beryllium, so they will be stopped because the attenuation coefficient is different. That's why here they clear mention. So neutrons are having the reverse qualities of X-ray and gamma ray. So for example, if you take a neutron radiography, so you can see the tiles, so you can see the rubber tiles, and also you can see the fuel content, and also you can see the leather sheet, and you can see the plastic frames, so plastic, rubbers, everything you can see the low dense material. But the same bike, if I take X-ray, you see only metallic portion like bumpers, wheel hub, and any metal rods, so that one only we can able to see. So this one is nothing but X-ray, and this one is a neutron radiography. Because the low dense material will stop all these neutrons, then we can able to see very clearly. Then how we are producing the neutrons? There are four ways to produce neutrons. So the first one is a nuclear reactor. So in the nuclear reactor you can perform some nuclear reactions and then you can produce the neutrons. Then accelerators. So in the laboratories research, so the scientists all they used to keep these kind of accelerators and they produce the neutrons. So then radioactive isotopes, same like iridium, gamma ray, or cobalt, cesium, selenium. So likewise you also can get this radioactive isotope sources. So one such source is a californium 252. So this is an important question in the examination. So californium 252 is one of the famous isotope for neutron radiography, and the fourth one is a subcritical assembly. Okay, you can see here. So when you produce neutrons, here they are using water. What happens? So the neutrons will be slowed down and they will be emerging as a beam. That is what we call as a collimation. You can see thermal neutrons. So when you get a neutrons, right, they are all fast neutrons, meaning the energy is very high. But when you fill with the water and when you pass through this water, what happens? The energy will slow down. So that process we call as a moderation, meaning you are trying to reduce the speed of the neutrons. So for that we are using the moderator, and then you need to have a collimation. So this one is area is a collimation through the collimator, so they will emerge out and expose the object. You'll see if you see in a nuclear reactors, so they call as a fuel cells in the nuclear reactor core. So they'll keep all these rods. So these rods are nothing but filled with the uranium capsules. They'll fill with the uranium capsules and they call as a nuclear fuel cells. Nuclear fuel cells, these rods. So what happens when you put inside the reactor, when you initiate the process, so they will release an enormous amount of energy. That energy is utilized to boil the water, and with the help of hot water they can run the turbines. How this is how they'll produce nuclear energy, like a nuclear power. Okay, most of the nuclear reactors they use the same thing. Then coming to the neutron sources, as I mentioned, so nuclear reactor you will get a very good intensity, meaning you can produce a high number of neutrons. So that's why when the neutron numbers are very high, you will get excellent resolution and exposure time is short, because here the energy is very high, so that's why exposure time is small. Then coming to the accelerator, 10 power 3, 10 power 6. But isotopes, you have only small number like 10 to 10,000 neutrons only you are capable of producing. So you are producing very small number of neutrons, so that's why it will take more time, and exposure time is long and the resolution also very less. But what is the one advantage? Portable. So isotope you can carry from any place, carry to any place. But when it goes to accelerator and as well as this nuclear reactor, mobility is very difficult. So if they ask which one is producing high resolution, so nuclear reactor is a high. But if they ask which one is a portable, so Californium 252 is a portable isotope. You can see here Californium 252. So Californium 252 is the most active isotope. So coming to the thermal neutron, so when you have a neutrons, right, so when these fast neutrons interact with the nuclear moderator, nothing but water. So for example, I put water here. What happens? These fast neutrons passing through the water and they'll become slow down. Again, they will interact with another atom and then it will split again, the fission reactions, fusion reactions. So if you know about a nuclear atomic bombs, all those things, so there will be several chain reactions. Because of that, it will produce explosions, right? So very high amount of energy will be released with these nuclear reactions. So here what they are doing, so they are just trying to reduce the speed of fast neutrons. For that purpose, they are using moderator. Moderator is nothing but a low density material. You can see here, for example, you are producing neutrons here, so the neutrons coming with very high speed, so we call as a fast neutrons here. So what happens when these neutrons enter into the water, so they'll get slowed down and they will emerge out here. This one is called as a collimator. Same, you can see here, so something like this divergent collimator. So you have a collimator here, so the neutrons is emerging out. So this is what we call as a process of moderation. So if you use a low dense material, the fast neutrons will be converted into slow neutrons. So which of the materials we can use as a moderators? This also exam point of view important. So we can use a hydrogen, water, beryllium, boron, carbon, graphite, paraffin. So these kind of low dense material can act like a moderators, meaning if you put these materials in its path of neutrons, they will be slowed down. This is nothing but wax, paraffin, wax, low dense materials. You can see hydrogen, boron, beryllium, carbon, nothing but graphite, all these materials. Graphite is if you see your pencil, that material is also like a graphite material. Then coming to the imaging techniques, there are two techniques. One is a direct exposure technique, same like your X-ray. Here also we are doing the exposure with the neutrons, only the difference is neutrons. But just now we seen, right, whenever you have a nuclear reaction, so there will be always a release of gamma ray. So neutrons, when you get a neutrons, obviously it will emit some radiation. So that is why here we have a gamma radiation. So but our title is a neutron radiography. I just found only neutrons. So what I'll do, I'll put a gamma filter. For example, this one is a small lead sheet. I put a 2 mm of lead sheet, for example. What happens? So this gamma will be blocked because gamma ray cannot pass through this lead sheet. So only neutrons can pass through this. So here you have neutrons and also you have gamma. But what happens? Gamma will be blocked and you are getting only neutrons. So these neutrons passing through the object and then interacting with this metal screen. So this one is a converting screen. Usually we use a gadolinium screen. So this screen interacts with the neutrons and it releases some energy in the form of light. So what happens? The film will get exposed. So here the concept is very simple. So the particles, nothing but neutrons, is a passing through the object and then interacting with the metal screen. Then the metal screen behind you have a film. So what happens? The neutrons will interact with the metal screen first, then after it will give some radiation to this film, then the film will get exposed. So this one we call as a direct exposure. Looks like same like a normal radiography. Instead of X-ray here, gamma ray, you have a neutron particle. So you have energy passing through the object and recording on the film. Once the film is exposed, then you process it. So looks like same like your regular conventional X-ray and gamma ray technique. How about the second one is called as a transfer or indirect exposure technique. So what happens here, like for example, this object is nothing but your cobalt 60 source. So the object is itself emitting the radiation, very dangerous. It is a radioactive isotope. So what happens? It is emitting the radiation. If I use a direct technique, what I'll do, like if I put a film and screen, what happens? The film will get exposed with this radiation because this is a radioactive material. So if you want to take RT for a radioactive material, so it's very impossible to use a regular film technique. If you put a film fraction of second, it will get exposed because too much of radiation coming out. So that's why they're using another technique called as indirect or transfer technique. So in this technique, what they do, they will use a small foil. that is nothing but a small metallic screen they will use. So what happens, the neutrons and gamma exposing this, and this plate will behave like a radioactive material because they're directly hitting with the neutrons. How we are producing isotope? When you bombard with a neutron, then the material will converted into a radioactive material. So here also what happens, so when the neutrons are bombarding this foil or this thin sheet, so this sheet behaves like a radioactive material. So once this sheet behaving like a radioactive material, so immediately they will keep with the film. So after processing the films, then you can get a radiograph. Okay, so here the concept is very simple. So just expose the screen first, then after you bring the screen to another room, then sandwich between the films. So this is a film 1 and this one is a film 2 and this is nothing but this foil. So what happens, this film will get exposed and this one also will get exposed. Okay, so that films we can use for reviewing. So what is the main difference between this direct and indirect? Here in indirect technique, the film is not exposing directly during the test. So you need to activate the foil. Then after you take this foil into the lab, then mix with keep together with the film. Then the film will get exposed. Right? So direct baby, and this one is a tube baby, test tube baby. So you might have seen the latest technology, right? So the baby born in a test tube. So how? They are doing something and making her pregnant, but that one is a direct, so directly. So you can see direct technique. So we are using this converter foil called as a gadolinium. So in direct contact with the photographic film is placed behind the object. Just now we mentioned, right? So when you are doing NR with direct technique, so you have a screen and behind this you have a film. So what happens, neutrons comes and interacts with the screen and the screen behave emits some light energy and the film will get exposed because neutron is a particle. So if you put a film will not get exposed. You need to have some converting screens. That is nothing but a gadolinium screen we are using here. So what happens, the neutrons interacts with the gadolinium and it will emit the light energy, then the film will get interacts. So it absorbs the neutrons and emit gamma radiation, and which internally is converted into the electrons. So not suited for gamma radiation emitting objects. So this technique we cannot use for radioactive objects because it's a direct technique. Because what happens, for example, if your object is a radioactive isotope, for example this is iridium 192. So what I do, here I put my gadolinium screen and here I put my film. So this is a radiation. So what happens, the radiation is passing through the screen because the screen is of 1 millimeter, for example. So 1 millimeter, so it will pass through the screen and it will expose the film. So you will not get information about this isotope. Your screen is getting exposed, meaning you are taking RT for gadolinium screen. So that's why this technique is not suitable for radioactive materials. So here you need to use a passbar plates or any other gadolinium screens, and your object is should not be a non-radioactive material. This one, for example, steel plate. Just say imagine this is one item object that you want to take NR. So the neutrons are passing through this. Okay, then they will interact with the gadolinium screen. So the neutrons interacting, then they will emit the energy. But here you have a film, just beside to the screen you have a film, so the film will get exposed. Same like your regular radiography, how we are doing, we have a LED screen and you have a film, right? Here in the place of LED screen you put a gadolinium screen, then you expose, same way, no difference. Then coming to the next one is a transfer technique or indirect technique. So in this technique, a metal foil we call as a dysprosium or indium or gold, these are three type of screens we need to use. Why? Because if they expose with the neutrons, they will behave like a radioactive materials. So they will start emitting the radiation. Same like gadolinium screen, but here they will give more information about radiation. So it captures the image by buildup of radioactivity through neutron absorption. What happens, for example, if I take a gold screen, so this is my gold screen. So what happens when it interacts with the neutrons? So it will behave like a radioactive material. So it will emit the radiation. Then after that, what this is what we call as activation process. So once the activation is completed, I'll take this screen inside the dark room. Then I will sandwich with a film. then my film will get exposed, right? So this technique we call as the indirect, because here we are not keeping film immediately, so we are taking this one to the lab and then we are keeping together with the film to expose. So that technique, like say like a test tube baby, right? You are doing something in the lab, then the baby is born. So that one is called as an indirect technique. So this technique is more useful for radioactive samples, and if you compare with normal technique, direct technique, it is a very slow technique because it is taking at least 8 hours for one exposure, whereas direct technique you can finish in 5 minutes. So you can see here, so this is one advantage with indirect technique, you can easily capture the RT for radioactive materials. Why we need to do all these things? Because if you see the nuclear reactors, you are using nuclear fuel cells, you are using plutonium, then uranium, all these fuel cells you are using to produce a nuclear power. So right, if you want to run any like nuclear reactions, other things, so you can use this NR technique, especially the weapons, nuclear bombs, all those things. So if they want to know the composition inside, like what material is inside, or how much they feel like explosive materials, all those things, only one technique is there with the neutron. You cannot use X-ray or gamma ray, so we only get more information with NR. So that's why this one is a more useful technique. Okay, you can see, so this one is a nuclear fuel cell. Inside these are all uranium pellets, uranium, right? So you see here the capsule is already broken, but if you take regular X-ray you cannot see all these things because they are already emitting the radiation. You cannot take X-ray, you cannot take a direct technique. So sometime if you take an indirect technique, you can able to see very clearly the capsule's location. And coming to the applications, so mainly you can use for explosives, especially nuclear fuels like atom bombs or nuclear bombs. So there they can use this one, and aerospace components, especially like composite materials. If you have any like water entrapment or any other critical locations, you can easily get. Or if you go with oil and gas, like especially if you want to see whether any gasket is present or any blockages, you can try with the neutron radiography because it can easily see the rubber gaskets in a thick material. Then adhesive component glue. Glue is a low dense material. Then nuclear control materials and nuclear fuel. Then NR is a powerful detection for the corrosion, especially in aircraft structures, and locating areas of water entrapment and hydrogen embrittlement, because water and hydrogen is a low dense material. If they are present, we can able to see very clearly on the radiograph. Same like a lead numbers, how you see the lead numbers clearly on the film, same way water or any hydrogen related things we can see on the screen. Disadvantages: expensive, high cost. The equipment is very expensive, and you need to go to the lab, not portable. You need to go to the reactors or accelerators. Then relatively large size, so you cannot have like X-ray, gamma ray, radiograph, like projectors, no hand carry on heavy equipments. And the personal protection and safeguard is very, because these are all particles. If they interact with your body, it will damage many tissues, other things. So that's why very dangerous. If you see in the factor also, it is like 20 times harmful compared with X-ray and gamma ray, and are not really portable. So same like gamma ray, you cannot perform NR. So nowadays they are doing something with the NR's portable units, but in the industry still they are dependent on these accelerators and reactors. But what is the main advantage? The unique information provided by NR outweighs all these advantages, especially the military, defense, nuclear related things. So if they want to get more information, they can make use of NR. Even though expensive, so they can compensate with its advantages. Okay, so this is about neutron